homeworks. There's old homeworks. I don't know if we're... Is that a lot of money?
No.
It's like in some other currency, it's 5 trillion or something that you can buy a cup of coffee with. Well, this is definitely, you're right on target, this money thing. We're going to sort of think about gambling and whether we can make more money or not, or when we're going to get more money, or what's the probability we're going to get more money. Would take all the fun out of it. According to the Spectator, many of you are engaged. You in the general sense are actively engaged in applied probability. There's a lot of applied probability going on at various tables and things around Columbia about lots of, various forms of poker, so forth. You can. It's sort of the TV has evolved, so you can do. If you have some interest, if you have one interest, you can focus on that interest 24/7. Like if you like to eat, you can watch the Food Channel, right? I mean, this sort of the Food Channel, and then you can watch the poker. You can watch the poker games. The main thing about watching the poker games, this is sort of some lapse of having some opinion about, is it's very misleading. You watch the people play poker because they kind of filter it down to the exciting moments. In order to be, if you do that in your spare time, you know that a key element in some form of success is to be able to put up with boredom. Okay, this may resonate. If you play cards and you want to do well, you have to show restraint. You don't jump in. But you watch these thing on television and you see all his hands are exciting. And then if there are 8 people playing, and there's usually 2 in the hand that are competitive, and it's very close, and they're actually showing you it's really some parts of our life are really pretty impressive for probability. Actually, there's 2 areas of this that are pretty good and that actually a lot of people understand and are engaged with. Right? And one of these is if you watch these poker games on TV, because they give you, as you watch the hand being played out, and these 2 guys are battling, and one guy has 2 Texas Hold'em, right? They're doing, and they're showing you the 2 cards. They're showing you their down cards, and they're showing you, what they have. And each card as it's played, they're showing you exactly the probability each one is going to win, which is that kind of interesting part, right? You see that, and you learn from that. If you don't know, I mean, I'm thinking from my perspective, it's pretty, it's accurate and it's computed, just like we do it here, and so you could understand, and that sort of understanding of the probability is to understand that. Of course, that's still only a small part of the game. Granted, the guy with the low probability may end up winning, may psych the other guy to drop out or whatever. But another place like that is baseball. I mean, everybody in baseball, there's all this stuff about batting averages, and people pay attention to that the player has a batting average of 250 or 350 or something, and you know, if people who follow baseball have a real sense of what there's a very high level of understanding of these statistics and their connection to the game. It's actually kind of remarkable. I mean, it's remarkable in relation to what it seems like understanding in a course like this. You'd think if somebody could understand those probabilities in baseball or in poker or something, that the rest of this stuff would be easy. But at any rate, just a kind of wrap. So we're thinking about, I'm thinking about sort of some sort of stock problem, and thinking like, and the stock is going to be modeled as Brownian motion, so that part may be, but you could think of having, a stock, say, and here you are, and it's selling today for $100 a share, and you have some number of shares that is sufficient to get your attention so that you care. And you want to know, let's say you might want to know a number of things. So it's, suppose it's, hopefully there's a drift upward in these stocks. Today it sort of feels like there maybe is a drift down. So you could be modeling this drift up and down as that's certainly a central feature. But it's somewhat, the Brownian motion is simpler. You can look at it with drift and without drift. The without drift is simpler, and you can do both. We'll think of it without drift. So you might be asking, so you have some time period, and maybe you're looking at one question. You might be, here you are starting off at time 0, the stock's 100. You might say, well, what's the probability that it goes over 110 before time t? I mean, maybe you want a 10% gain, and you're maybe even planning, as soon as you make your 10%, you're going to sell whatever. So you want to know, you're sitting here and you're moving along, and then boom, it's made that. You want to know if in fact this does this, or if it, alternatively, if it does, and so forth. This might be not so good, but I mean it might do this. So you might want to know probability that the time it hits 110 is less than or equal to t. So this is the time, hitting time. One question. Okay, let's see. So, well, a related thing. You might be even a little bit more sophisticated. You're sitting here at 100, and you want to know. You want it to go to 110, but it could be 80, or so hopefully evenly spaced. So that you might want to know the probability that it hits 110 before it hits 80. So you want to know, it's going to go up and down, but you want to know what's the probability that it goes up 10 before it goes down 20. So this is sort of like you're going along, and maybe in this case it actually does this, it didn't quite make it down here yet. So this is kind of like okay. So but you're going on. Now you might also want to know something like, you know where you are. You started at 100. I don't know, this is a little less that you want to know it maybe, I don't know. So here you are, you got to 120 here, and this is where you are, and you might want to know, well, where were you at t over 3? What happened here? You know you're here, you're here, what's the conditional distribution of what happened in the middle? Okay, these are things we're going to do. So, and And well, we want to use Brownian motion, but there are actually two fundamental questions in this picture. Sort of one is, is there a drift? Are you going to go up or down and so forth? That's so. Maybe we might assume there's no drift. Then there is another major question: is what is the volatility or the variability in this? How much is it doing this? I mean, if there's no drift, the Brownian motion has a kind of simple symmetry. You're kind of going up and bouncing around. Without drift, you're bouncing around, and it's only the rate, the kind of how much change do you expect to have over any time is sort of a basic model. So you might think, well, if, yeah, this might be, say, this is 3 months. So this is 100 days, say. So we might think, okay, so I'm going to talk about these things. But so there's part of this, it's not just, I don't want to just say, well, this is Brownian motion, and what will all this be with Brownian motion? Actually, well, that's what chapter 10 is about, and that's what I do want to say. But actually, if even without a drift, there's a sort of, there's an issue about how fast, how much change is going on as a function of time. What rate is things fluctuating? And if you thought of it in terms of days, 100 days, you might think of the change. So you might think the price at day n is 100 plus x1 plus xn, where these x's are IID, and we're making them have mean 0, and variance, this is the important part. So this is a kind of discrete story. I'm just going from day to day, so I'm not actually in this picture yet. I've actually said, I'm really thinking, well, this is sufficient here. I may be thinking I'm dividing it into days, and I'm kind of just looking at what happens when I go from day to day, and I'm not doing it in continuous time. And yet, if it was a stock, you'd be actually moving in continuous time, or at least while it's trading. I mean, there might be something, maybe if you're assuming you could trade 24/7, it's just going in continuous time, evolving. But as a simple thing, if you think of it just per day, you have this discrete time model, and this is the drift, and there isn't any drift, so it's got mean 0. But what I'm focusing on, well, then there's a question of we've actually put one element of time as day, per day. So there's some variance. This parameter, variance per day, is going to say something about variance for 100 days, right? And so in particular, when you want the variance of the price at n, that is going to be n times sigma squared, right? In other words, the price at day n is 100 fixed, plus the sum of n increments, which are independent and identically distributed, each with variance sigma squared. So the variance of the sum is the sum of the variances. So at 100 days, if the, let's say, the variance, for simplicity, suppose the variance is 1. So each day, we're thinking each day the variance is 1. Standard deviation is 1. So stock is kind of like maybe going up and down 1 on a typical day. But at this time then, at t, the variance, let's call it x of t, the price, is then t, and therefore at variance 100 days, the variance is 100, which is sort of reasonable because variance is 100, standard deviation is 10. So we're talking about, you're at 100, one standard deviation in 100 days is plus or minus 10 if it's plus or minus 1 standard deviation, undisturbed. Of course, this model, an important problem with this model that actually leads to some different model is the fact that you're going up and down and there's no reference to this 0. right? I mean, the model assumes you go up and down, the increments are IID with some distribution, and no matter where you are, well, as you get close to zero, the closer you get to zero, that's getting very unrealistic. Because obviously, well, you're not going to go negative to begin with. But also the amount of change is typically proportional to the price. So if the stock is selling for 10, it's going to change less than if it's selling for 100 or even more. And that's really, realistic models are different for that reason. But if you're assuming you're sitting at 100, that isn't too much. You know, you may be going between 80 and 120, so it's not too crazy to assume that. Well, all this follows the pictures that we went through yesterday. If you have this sort of thing, you have a random walk where it's discrete time, once a day, but these changes are random during, and they could have any distribution at all. And by the central limit theorem, as you get many steps, this is going to be these increments over several of these are going to be normal. So if we do something, well, so when we get Brownian motion, we're going to take this sum. So Sn is the sums. But we're going to take those sums and scale time so that there's n of them in time t, and divide by square root of n. So we're going to construct a continuous time. For any given n, we're just putting n steps in time 1. But when we have many steps, but we make the size get smaller. So this is the daily change. The daily change has some distribution with mean 0 and variance sigma squared. This thing, if you look at this expected value is still 0, but if you looked at the variance of this, you'll see that this is the integer part of nt. So ignoring that non-integer part, the variance of the sum is the sum of the variances, so that's nt. This is nt terms here. So we've shoved time together, but we've divided by square, and then when you multiply by or divide by a scalar, the variance is just the square of that. So this becomes t. So this is a scaling that you do with these random walks. You scale time by n and space by square root of n. And then the variance comes out to be something. If you scale some other way, the variance is either going to go to 0 or infinity. So you scale time by n and space by square root of n. And that's because the variance of a product, you know, the variance of, we're using variance of cx is c squared variance of x. So that part is square when we do this, but when we add up things, the variance of the sum is the sum of the variances if they're independent, the random variables. So the additive part means this becomes proportional to n, whereas the multiplicative part, this becomes n, which forces n scaling here and square root of n here. What we're doing is we're thinking of, well, the daily change has variance sigma squared. Suppose we now change our units and we want to talk about change per 5 minutes and change in continuous time. So if we put more and more, if we scale time, we're going to make the changes smaller, and we're going to scale down so that as n increases, we're having small change, infinitesimal change in infinitesimal time. So that means in this picture of Brownian motion, you're going to have the variance of x of t plus s minus, let's call it b, it's Brownian motion becoming, b of s. So here's an interval of length t, and this is going to be sigma squared t. Yeah.
Split the time into, that the variance of 1 is 1?
Over here I put this here, so I'm sorry. I've put this here, which is a realistic thing, but here I'm still leaving, so yeah, I should still have the sigma squared here. Whatever it is, and if it's 1, I wouldn't be there. Yeah, so if I have the sigma squared there, if the x is, this would be, if this is sigma squared, one part of it was assuming it's 1. So the variance of x, but there's this many of them, right? So this should still be here, but which would be 1 in our example. I don't know if I'm... So if it's per day, you're going to end up with the same sort of story of, for any interval of length t, you're going to have the variance be sigma squared t as the model. And what's happening, because all of this was random walks, you have these increments as you move around this part of the story. So you're looking at the model, and here you are at 100, but you're moving around. And so this increment, you change from here to here, or over here you change from here to here, right? So this is going up here, and in this case you're going down here. This increment involves the increments in here, and this involves them in here. And since these came from independent random variables, the increments are independent. And they only depend on the length. So the distribution you're having it have a lot like a Poisson process. The change over disjoint increments are independent, and they depends only on the length of this interval in the sigma squared. So that this, if we pick here s and s plus t, the x of b of t plus s minus b of s is going to be normal 0 sigma squared t. The distribution of any increment of length t is going to be normal, and there's no drift, 0 drift, but it's going to be proportional to t, the variance, and we're going to have some sigma squared here. And what you're doing to fit this is kind of from this random walk. The association you want to make is that many of the real things would be discrete time, and there'd be some rate at which this variance occurs. And this, over 100 days, you would get, with sigma squared times 100 would be the total variance. The same thing would be with this Brownian motion. In other words, the random walk is, each day has variance sigma squared. So over 100 days, the total variance is sigma squared. I mean, its total is 100 with this, 100 sigma squared, or if sigma squared is 100. The Brownian motion would be exactly the same thing, it's just continuous time. So that the variance from 0 to t would be the same. You're just kind of putting in a continuous time thing of the same thing. So the point, one of the parts of the main message from Tuesday's slides were that if you started with random walks, it begins to look like Brownian motion. So then the transition we're going to make is we're just going to look at it as Brownian motion. But the kind of real thing to think about a lot is random walks, that you're seeing a random walk. Okay, but anyway, the price of the, if sigma squared is 1 here, then we think of this thing as standard Brownian motion in this case. So this is standard Brownian motion. That's mean drift 0, and the sigma squared is 1. And if we have, in general, let's say we want another Brownian motion general with parameters mu and sigma squared, this corresponds to taking, if you call it x of t is equal to sigma. So all you're doing is scaling. If you add a constant function of time, that's giving you a drift. If you multiply by sigma, that's giving you a variance. So if you started off with standard Brownian motion, you get Brownian motion with drift mu and variance, or sigma squared, by just doing this. That's a lot. This is a lot about what chapter 10 is about. The point here, it has stationary independent increments, and the increments are normally distributed. Then you start wanting to do some computations like we talked about. Okay. Okay. Let's see. So suppose we first talk about the probability that we hit 110 before t, which was 100 days. So this picture here. We want to know we started 100 and we want to go up 10 before 100 days. Okay? Now there's two parts to this. One part is this: the increments of this Brownian motion are always normal. So all you're doing here, you're doing tons of calculations with the normal distribution. So if you've avoided it up till now, you can't escape. You've got to do it even more and more normal distribution calculations. But otherwise, there are some very nice tricks, and actually the tricks go beyond that to whole theory. But anyway, so let's first discuss this, where we're thinking of this. Here we are at 100, 110, and we're thinking here's the t, and we want to know, what's the probability that we get up here? Okay, that's our hitting, and we want to do that before time t. Well, here we're going to, this part is constant. From the Brownian motion point of view, we regard this as 0. And so we're going up 10, so we could think of this as now 0, and we're going up 10, and we're ignoring this lower barrier. Brownian motion is not paying any attention to the lower barrier. It's just moving along here. If you're starting at 0 and you want to go up 10, then this would have been minus 100. The chances of going down here are not very great, so it's okay to ignore it practically. But this is just moving around without any reference to any barriers. Okay, so the first thing that first trick, is the reflection principle. And that's sort of, well, you could think of the following thing, that if you hit here, you're going to have been, well, okay, so then you could be here, or you could be down here. So, well, let's see. So whatever happens, you've hit here. So after you hit here, you could go up here. You could do anything. Let's say you could go up here, or you could go like this, back and forth up here or down here, right? So the path after you've hit, you could do a variety of things. So the thing that this process have, because everything's normal, the normal is all symmetric. So let me just put one of them here. Put one of these. One path might be this. I hit here, and then I do this, and I end up here. There's a corresponding reflected path that is down here that just takes and flips it over, that has the same probability as this path. Of course, each path individually is probability 0, but the density of it would be the same. So that if you start here, you could have done this, and then the minus the process has the same distribution, so you could have done this thing that ends you here, where this is A and this is minus A, right? So the reflection principle is, if you think of you can then consider that if you hit, given that you've hit, you're going to end up above with probability 1/2 and below afterwards with probability, same probability, above and below. So, okay, so that's this thing. So then we want to, so if you hit, you could end up here. And so that the point that you would see is the probability that ta less than or equal to t is twice the probability that x of t greater than or equal to a. This is the one trick, the trick of the moment. You want to say, what's the chance, what is this hitting time? Well, the thought is, okay, one thing you could talk about, the probability of being up here. If you end up here, for sure you have to, the paths are continuous. If you end up here, you have to cross this, right? So that's part of this, but it's not the whole thing. You could have hit this and gone down here. But this is part of it. If you hit up here, that's one of these. If you hit up here, that's, you certainly hit. And the 2 is to count the other cases. So for every case that you hit up here, for every path that comes up here, there is precisely one path that's reflected with the same probability that hits below. And you either hit above or you hit below. So the lower part where you hit here and then go down is matched by the ones where you go up. And they exactly match. So then the one going up is totally this, and the one going down is equal in probability, therefore you have this. So this is then easy, because this is the probability that, twice the probability that normal 0t is greater than or equal to a. Because these things are, this is going, this x of t is going from 0 to t. And if sigma squared is 1, we're doing standard Brownian motion. If this is standard Brownian motion, put b of t. Standard Brownian motion, it has variance t. And so then you just have this. And if you wanted to convert it to, you could proceed, if you're looking up in the table, you would say that's square root of t, normal 0, 1, greater than or equal to a, because variance t is the same as multiplying by the standard deviation, which is square root of t, and then that's twice the probability normal 0, 1, greater than or equal to a over square root of t, right? Whoop. First we have what's the key thing, which is not obvious, is this reflection principle. Given that this Brownian motion is normally distributed with variance t, so you've got this, and you want to write this in terms of normal 0, 1 in order to look it up in the table. So you just say, well, variance t, if I take square root of t out, that becomes square root of t. This thing has the distribution of the standard normal times square root of t. Because this is variance t, and when you multiply by its square root, that means this has variance t as well. And so you've got this, and then you put the square root of t down here, and this is what you'd look up in the table. You'd see the probability that the standard normal is bigger than this. Okay. Let's consider this one, which we were starting to talk about. Here you are at 100, and you're going to go to 110, so it's 110 before 80. Have the bottom. So here you are, and you want to. So this is the probability that you hit 110 before you hit 80. This is the time to hit 110, the time to hit 80. So as you go along, you have this path. There will be some time where you cross this, and there'll be some time where you cross this, and you're assuming that you get to 110 before you get to 80. And it's all symmetric. It ought to be, the Brownian motion is symmetric, but notice that your target is only 10 up, but it's 20 down. So it ought to be easier to go up than to go down. Right? That means just intuitively. So this is, again, like, it's a little bit like the Poisson process. The obvious answer is the answer. So there's a lot of this. So the point is, what should the answer? What would you think the answer would be? I mean, if you look at this, this is 10 away, and this is 20. So it's twice as far away to here as to here. So you're more likely to get here somehow. And if I made this closer, it's even more likely. And if I make this further away, it's even further. And that's because no matter where you move, you start over, right? The future is always looking like a new Brownian motion, right? Because its increments have mean zero. So this thing's got all this independent increment. So if you did get to 80, you would then think of going to 60 and so forth. You could think of this repeated. So what should the answer be? What should this be?
4,
Yeah. What?
2 or 3.
This is right? Right. That's what it should be, and that's what it is. Yeah. So that should be clear, right? That's sort of, I mean, and then you want to go to here, but it should be this distance divided by this. The further you make this away, the bigger it is. I mean, certainly in the right direction. You might think it's not so nice, but that actually is. Now there's two sort of basic ways to see why that's the right answer. One way is to look at back in chapter 4, which we didn't pay much attention to, the gambler's ruin problem tells you in simple random walks what this is. Gives you some detailed formula. There's actually a much better thing. There's a whole theory of tricks that we're going to talk about a little bit, because it just seems like this is actually such a nice concept. You should know something about it. This is actually a word that, this is a word that's closely related that people think of as having to do with making money. So, martingale. Okay. So actually, Ross doesn't have, in this book, there's no chapter on martingales. You could have a whole chapter. Ross actually talks about this in the problems, in the exercises. So there are something like 6 exercises in the back in which he defines martingales and does a little bit. So it's actually one part about it, there's not much there. You could look at other books, but what is there is certainly gets a minimal part of the story. Okay? Now, and this problem wonderfully illustrates what martingales do for you. And the thing that's really nice about this is its strangeness, in that this is a type of stochastic process. You know, each of these chapters, to some extent, are a type of stochastic process. Well, martingales are just sort of defined totally differently than all the stuff we've talked about. So it's really kind of nice even just to think about it for a second and see it's a definition of how the stochastic process evolves that is, well, at first, confusing. I mean, there's a definition of stochastic process. So we're going to say x of t, we're going to have the stochastic process, could be discrete or continuous time, and we're going to say is a martingale if, and well, we're going to have the expectations finite. This is just a technical condition. Technical. We want to have all the expectations finite. We don't want to have any trouble because we're going to define how this process evolves by looking at its conditional expectations. We're going to assume that if we condition on, say, let's condition on x of s for, well, maybe x of u for 0 less than u less than s less than t. So we're actually, we've gone along, and here's t, and here's s, and we're conditioning on all of this up here, past. It's like Markov chain, right? Markov chain, the probability. So if this was not expected value, it would look like the Markov property. The Markov property would say the distribution at t, conditioned on everything up to s, depends on the distribution only at s. right? That's Markov property. But this is just giving you the conditional expected value. There's no Markov assumption and no independent assumption. Just this assumption. The condition, well, I haven't said it yet. The expected value at t, given the past up to s before t, is where you were before at that point. Okay? So you're moving along, and you know everything up to here, and you've got here. You did something, and you're here now. And you want to know where your expected value in the future is going to be. It's going to be right where you are now. Independent of this, but it's where you are now. It's like you're gambling, you're playing a fair game, and you've played a whole lot, and your current, earnings is such and such. You have so much money at this instant. You did a whole lot of past stuff, and you're thinking, what's going to happen in the future? And if it's a fair game, your expected value in the future is just going to be where you are, no matter what. So it's sort of like a model of a fair game where there's no tendency to win or lose. At any given time, conditioned year, the future looks, the expected future position conditioned on the present and past is the present position. So that's this. Now, the immediate relevance is Brownian motion is a martingale. So that's nice. Yeah.
Say your expected future position is where you are now. You mean it's the value of where you are now? Or
This is the value of where you are now. That's right. So if we were doing this, we're going along and we stop at any place, like we just pick here, and we're saying this happens to be S, this happens to be T. We're saying, oh, this could have any pass. I condition on all this stuff up to here, and I say, where am I going to be here? What's the expected position? Well, the expected position is right there. That's the expected position. Of course, it's going to do something, but we don't know. But it's no matter, and wherever you look in here, if you stop at any S and you look at any future and you condition on the past, the future, expected future position is just where you are today. This is like you play a whole lot of weird games. So this comes up like if you think of whatever you do is complicated. So like the place where this comes up is if you're doing some gambling and you have a strategy like, I've gotten to this point and I'm playing this fair game, but if I'm going to double, if I lost, I'm going to double my bet or such. These kind of issues about complicated gambling strategies. If you're playing a succession of fair games, this is going to mean it doesn't matter, you don't have to have the same game. You can change the game every period and whatever, but if the future if it's a fair game going forward, it's going to be wherever you are. Your expected value is going to be wherever you are. So, yeah. But this is sort of reasonable, but it's not saying anything about the distribution. A martingale is just a stochastic process with this property. So a lot of the processes we've looked at, Markov chains and Brownian motion, can be constructed. You can look at related processes that have this property. But this is a definition by itself. So you could say, well, I have a stochastic process. It's a martingale. What can I say about it? And there's a huge theory of stuff about martingales. And it's very powerful. And one of the best applications is to this problem here. So this is maybe the easiest and best application. So one of the main theorems, and this is actually complicated, and this is a theorem, the optional. Well, it's the stopping theorem. So we'll have a stopping time, which has actually got some technical properties. And then if you have a stopping time, and if some more, you're going to have x0, xt. At this random stopping time, this will be a martingale. Now, the important point is that you're going to have So I guess one of the things I should point out here with this martingale definition is if your expected value at t given the past is up to s, is x of s, its expected value of x of t is just what you were. If we uncondition, it's the expected value of xt has to equal where you started. Just the straight and unconditional one, which is like to go make this a special case where s is 0. And so this is like if I have a simple martingale, it's just 0 and t. I mean, the expected value of my final position is this first position. Now, the stopping time this is a random time, but it's supposed to, if you stop at n, it's supposed to not depend on the future. It's a little bit complicated, and there's some technical conditions, but you have this property, that if you stop at a random time where the stopping time doesn't, depends on the past, it depends on the history. So you make a rule, like how you're going to gamble, that tells you when to stop. And here we have such a rule. Our rule is we're going to stop as soon as we either hit 110 or 80, whichever happens first. So we start at 100, we move along at this random Brownian motion with no drift. So wherever we are, the expected future, it's got this martingale property because we're moving along and we're sitting here. The future is just another Brownian motion looking here, and so you happen to go down or whatever, but your future looks the same. So this property is all there in the Brownian motion. But now we want to look at the time. The stopping time is the first time we hit one of these two boundaries, which we could define as, right, the minimum, 110 minimum, hit 110 minimum t 80. A stopping time is the minimum of the time to hit 110 and the time to hit 80, this way. So we'll take this as a definition. So that's our stopping time. So let me and then once you have, there's actually lots of processes that are martingales, so you can start computing everything in sight. But this becomes especially interesting because in this problem, you have the following, that the expectation of, in our case, it's Brownian motion, and at this time is the Brownian motion at 0. So I'm forgetting that, let's call this 0, but this is the 100, the 100 taken out, right? So the Brownian motion, there's always 100 added, but now the expected value of the Brownian motion at this random time, is just where I started. So I'm looking at the change from here. So it's either plus 10 or minus 20. And this is the martingale property. It's saying that the expected value at the random stopping time is the same as when I started. That's enough to give you this. Right? Because you're going to say, I'm going to be either plus 10 with probability p, some unknown probability p that we want, or I'm going to be minus 20 with probability 1 minus p. This is the change from 0. I either go up to 110 plus 10, or I go down to 80 minus 20. And this, I go up. This is the up probability p. This is the down probability 1 minus p. And that change has got to be 0. Or if I added 100 everywhere, it would be the same equation. If you solve that for p, you get p, 10p plus 20p is, if we rewrite the thing on the left, you'd get 30p equals 20. P equals 2/3. This is just the beginning of these martingale tricks. There's tons of little martingales you can assign. You'll see some of that in Ross, that you can start calculating all these probabilities of what happens at these random stopping times, what the distribution will be. So that you get, it all makes, it's totally intuitive as well, but this is pretty powerful that you just compute. You make an appropriate martingale. In this case, it's just Brownian motion itself, and you have a well-defined stopping time, and when you compute the expected value, you know what it is. So this is in the spirit of all this stuff about derivatives and option pricing and so forth. All the finance is full of this stuff about when are you going to buy, sell, and so forth at some random time when the thing does something, martingale is very powerful. Yeah?
How it used for non-standard domain?
Yeah, so if you have, you're thinking if you have you end up with different, you're going to end up with different, there is indeed a whole thing of tricks which are different. So if you say, if I add linearly, one of the things that, so there are, let me just say something a little bit. So we have Brownian motion. Here's a martingale. And then you have this as a martingale. This is Brownian motion minus, so it's, what am I doing here? Should I have squared here? So this thing is its variance effectively, but this is the variance, but then the variance is t, so get this thing. And I'm going to have exponential martingales and so forth. So I'm using these different martingales, and I'll be doing the same thing. So you're going to be doing, this is the sort of Brownian motion itself is a martingale, but there's quadratic martingales, exponential martingales, so forth. And so essentially all you're doing is you take one of these alternative martingales that's exponential, some function of the martingale, just compute its expected value, boom, out drops these formulas. It's really, I mean, that's a high-level thing is you just got the martingale. The process itself is one martingale, but there's all these functions of the process that are also martingales. You just take the right, and the quadratic and the exponential ones are the obvious ones, and you just compute their expected value. And at the random time, you're going to end up with an equation just like this. I mean, at high level, this is the same thing. So you actually do this for a lot of these problems. This part of the story is actually good to know. I mean, if you know about martingales, oh, well, there's this definition of a stochastic process that says the future, the evolution is determined, is constrained or defined to be that the expected values are saying your expected future is going to be where you are now, whatever that is. That's the definition. The other part of the story is this. For some sort of martingale there, you stick in this random time with appropriate definitions, you're going to have this. And you start doing this to all these functions, and you start computing things just like this drops out immediately. And you don't do anything. You remember, we didn't analyze how the thing evolves elaborately. This is, once you write this down, this is about as fast as you could imagine. But it sort of looks like the right thing because the problem's simple. It's sort of got a full of symmetry. Okay. You're going to get your chance to do some of this. Let's see. So I want to do one more thing that's seems to be, we can fit in here before the L word. Here we are t, here we are 0, here we are at 100. And maybe we've gone here and we've gotten to 120. We started at 100, and here was t, and so we might say, well, t over 2. So the thought is now we're kind of looking back. We know where we started, we know where we ended, and we want to know where are we in the middle. Not sure why you'd want to know that and why you'd want to know that right now. Too compelling, but so this is right at the beginning of Ross. So this is there. I think that if I talk you through this, it's got to help somebody. So this is actually like on page 2 or 3 of the chapter, but it's a little confusing. So the point here is everything inside is normal. So let's call this S for some. That fits the book. So not in the middle. In the middle, if you thought of where should your expected value be, everything is like you think. If you ended up here, went here, you draw a line. The line connecting here and here, that's the expected value, right? That's what you'd expect. There's sort of no extra information, so the expected value is here. And the more you get close to one of these things the smaller the variance gets. Right? So if you think the expected value is on this line, inside. You're given this, you're given the values here, the expected value is on this line, and clearly as you get close to the endpoints, your variance is going to 0. So the variance, as you might guess, looks something like S times t minus s over t, I guess. I got that right. Okay, but at any rate, that may be important to remember that. But you want to compute, so you want to compute the density of x of s, b of s, it's Brownian motions, b of s, given b of t, and this is at x, and this is at, well, it's plus 20, right? So this becomes 0, and this becomes plus 20. And you want, so you want this conditional distribution at s given where you are at t. Okay, so this is all in terms of densities because we've got densities here. So it's just, I'm using this formula. Definition. The conditional density of x given y is the joint density of being at xy divided by the density of y. So this is the thing you have to remember, this formula about conditional density. So that's all we're applying. However, here, these things are all normal. Joint distribution's normal, so forth. So you could be, where are you at t and at s and so forth. So this is the basic formula. So let me go back to this b of s and b of t. You want, I guess, x and, well, so it could be y there too. Now, what we want is this. Right, so now we have these particular random variables that are Brownian motion. So we know this is normal here, and we know this is normal here. The problem is with this. The first problem is we want this joint distribution. This is a little complicated because this random variable involves this random variable also. In other words, this is from, the first one's from 0 to s, and the other one's from 0 to t, so this part's counted twice. And that's a complication. They're dependent. You would like them to be independent, so you could write instead this. So all I'm trying to write this joint density down of what b of, these are each normal, but the joint distribution's messy because they overlap on 0s. So instead I write the first one unchanged, and I look at the difference of the second. So if b of s is x and b of t is y, that means that's exactly the same thing as b of s is x, and this difference is y minus x. And now these random variables are independent of each other because they're disjoint intervals. So first of all, I've got this definition of conditional density. Secondly, I've broken this thing into variables that are independent of each other. So those are sort of conceptual parts. Then you're left with, this thing then becomes, if we put it here, FBSX. They're independent. So now we have three separate densities. Okay, first conditional density, second separate into two independent components. Since they're independent, we have the product. Okay? Now, actually, that's the easy part. As is usual, the hard part of this problem is to do the basic probability. The hard part is you plug in the normal density for these three things. Okay, conceptually this is pretty easy. Up to here it follows logically. Now you just got to do the nitty-gritty to plug in the normal densities and calculate what you get. And that actually is quite tedious and unpleasant. Okay, and Ross does this, and it might be confusing. So in part, of course, the key thing to know is that when you do all of this stuff, and if this joint distribution is normal, and these are normal, and everything inside is normal, that this density itself is going to be normal. Okay, that's the final result. It's bad enough to know that and then still be able to, so it's conceivable that I will have to sneak through to lunch before I actually do that. But but the point that you know, that you want to know that, well, if these are normal, so is this whole thing. And now then, what do you have to think about the norm? What are the normals? So let me just write them down here. 1 over 2 pi s e to the minus x squared over 2s. That's because they all have mean 0, but the variance is the length of the interval. So the variance is the s that goes in the normal density function. And the second one is going to have 1 over 2 pi t minus s e to the minus y minus x squared over 2t minus s. Now, that's because this is distributed the same as this. The increment between t and s is the same as 0 and t minus s. So this is distributed the same as that. And then you have down here right? So you just plug in the normal density with variance s, the normal density with variance t minus s, the normal density with variance t. Just plug those three normal densities in there. This is actually not, I'm maintaining this calculation here is the part that is confusing. It doesn't seem so bad. Actually, if you know it's normal, everything's got, you've got to get the mean, but if you know it's normal, you can be doing something for yourself. You can say, well, let's do this. Let's look at this. I'm just taking these square roots. I mean, because it's normal, it's going to come out with 1 over square root 2 pi variance, whatever that is. So you can actually read that off here and see, well, the 2 pi's are all, but you're going to be left with 1 over square root of 2 pi. And then you've got an s and a t minus s and a t. So this is the variance. That's because I know it's normal and there's going to be one of these. I mean, I haven't proved it all yet, but if I know it's normal, I've got that in a leading term. Because the density is going to look like the normal density in general is 1 over 2 pi sigma squared e to the minus x minus mean squared over 2 sigma squared. So I'm looking for this parameter and this parameter. So if I just do this, I'm going to see that I get this. I mean, I'm knowing it's normal. And the rest of this stuff in the exponential, if it's not normal, would not come out right, and all this would be not correct. But if it's given that it is normal, I've found this sigma squared. Okay, well that's just to remember that actually variance is s t minus s over t, and you see that indeed as s gets close to 0, this becomes small, and as s gets close to t, this is small. Now, what Ross does here is good. He's now going to actually do the kind of dual of what I just did. Instead of focusing on all those square root factors in the front, he's going to focus only on the exponential, and he's going to focus only on the things that are functions of x. So he's going to pay attention to what's functions of s. None of that was the square root stuff. All this stuff doesn't have any x in it. So he's looking for a function of x. He's going to collect the terms in x. So he's going to write this thing down, which we're getting here, just put equal. He's going to put some constant, and then he's going to collect the terms in x. And then he's going to have e to the minus x squared over 2s. And then e to the minus y minus x squared 2t minus s. So he just got rid of this, no x. I mean, and now, of course, the thing is, he's going to produce something like this, which he's going to have to, it's going to have to integrate to 1. If there's a constant there, the constant's always free. If you produce a function of x with a constant in front, it's going to integrate to 1, and you've got the right thing. So he's just keeping that constant free, but it makes instead of having 3 of these to deal with, you only have 2, because x only appears in those 2. So you're collecting x. And then, okay, so you then write this as the same thing. So this is for some constant. And he doesn't care what it is, because in the end it's going to be integrate out. So then you have, this is exponential, and then you can group them together, x squared over 2s plus y minus x squared over 2t minus s. Okay, and then you're going to group this stuff. You're going to have x squared over 2s plus y squared minus 2yx plus x squared, I should have minus everything here, over 2t minus s. Okay, we got this. Now, this is sitting here. So the point is, this is sort of not straightforward. I guess the main thing to emphasize is the idea that in working with this, instead of doing the whole thing by brute force, he's saying, I'm only going to pay attention to the terms in x. It's not a natural thing to do. The natural thing is just to grind away on the whole thing, and it's messy. So this is sort of like, I'm just emphasizing. This sits there right on this page, and if you just see, well, it's this. And so when he gets here, he's going to throw this term out because there's no x. And he's going to then change the constant to whatever, k1, k2, k3. You don't even notice that as he's going down the things, he's got these constants there, but they're changing because he's taken every time there's something that doesn't have x in it, he just throws it into the constant. I mean, that's not such a big thing, but this step is actually, this is actually harder than the main idea. But so then you're proceeding, and you've got e to the minus x squared over 2s, and you've got an x squared over 2t minus s, and you've got a plus 2 yx over t minus s. Okay, and you proceed. But once you've got this, you're in business. This is a new constant. We threw this one out because there was no x there, and we group these terms here and so forth. And you're going to get, this is going to proceed, and you're going to end up with, if you do the same argument, you're going to end up with so the point is, we know this is the variant, so I've just plugged it in here. And then we know this is the mean. And that algebra is just going to get you here from this point. But the simplification makes this algebra easy, as opposed to the whole thing head on. So that you're going to get this, which is the normal, and then the 1 over, there's some other constant here, whatever it is. But it's this, and so it's going to have to be 1 over square root of 2 pi st minus s over t, because that's what goes there. So you're actually just grouping all this stuff together in here to get this. that may not bring joy and happiness to one and all. Okay, the thought, we're at the L word, but this is sort of to capture. This is a little bit odd. There's a perspective change when you come to this chapter. Brownian motion is in some ways very simple, and yet it starts involving different notions. The thing could be it takes a different tack on the whole thing. So this stuff, you start doing all these calculations with the normal distribution, it's messy, so it can actually be confusing, but there are these tricks there that once you learn it, that actually stuff is very simple. But there's a little bit of setup. But this business of the martingales and the Brownian motion is a nice thing to learn as something different, even though we're not doing it in great detail. And I guess a reasonable attitude to take is to know that this is a small sample. There are whole books on each of these topics, so it's an endless pit of stuff which you're not trying to learn it all in this time. Okay, well we'll do a little bit more next week. Homework is being collected. Homework has gone around back. There was a homework coming back. If you didn't get it, there's a collecting.